Hello everyone, today we're going to be looking at some problems from the MIT OpenCourseWare course, Multivariable Calculus. Just some details on the course. This is taught by Denis Auroux. It was taught in 2007 and you can find it on MIT OpenCourseWare's website. Now the problems I'm going to be covering are from problem set 1, part B, and there are problems 2 and 3 in that part. So I think we can just get started. This is mainly to do with vectors and a little bit about matrices and determinants, but not really that much. So let's start with problem 2. Let part A. Let v1, v2, and v3 be the vectors in the plane from the points p1, p2, and p3 respectively to a point P. Express in terms of the dot product in these three vectors the condition that P is on the altitude of the triangle P1, P2, P3 from the vertex P1. By altitude we mean the entire line. That's just a note saying that they mean the entire line here. Oh, well, ignore the terrible triangle. The entire line instead of just this segment. And so why don't we try and find out what this means, alright? So basically, if we have a triangle, and I'm purposely going to draw a scalene one just so that we don't lull ourselves into a sense of false security by using like an isosceles triangle. Okay, there we go. And so if this is P1, P2, and P3, and we have a point P which is on this altitude, I'm just going to draw that in red actually. So we have vectors v1, v2, and v3, and we have to find out what are the conditions for this point P in terms of v1, v2, and v3. And so this part is pretty simple because we know that v1 has to be perpendicular to this line, and that line you'll notice is just v2 minus v3 or v3 minus v2, but I'm just going to take it as v2 minus v3 for now. So in other words, the dot product of v1 and v2 minus v3 is going to be 0, or v1 times v2 minus v1 times v3. I haven't labeled them as vectors, is going to be 0. Now let's go to part B, because we've essentially expressed this as a condition, right? So we don't need to do any more here. Part B says, assume P is at the intersection of the altitudes from P1 and P2. Show that V1 times V2, V1 dot V2 is equal to V1 dot V3 is equal to V2 dot V3. So we know that V2 dot V1 minus V3 is going to be 0 because V2 has to be perpendicular to, and so if we draw this line, then it has to be perpendicular to this line, or V1 minus V3. So we can take this here. So we know that V2 V1 minus V2 V3 is equal to 0 as well, and we know this here from earlier. And so we can write V1 V2, I'm forgetting my dot products, V1 dot V2 is equal to V2 dot V3 from here, And from here, we know that v1 dot v2 is equal to v1 dot v3. So and there we go. That's what we were looking for. So now let's go to part C. Under the assumption in B, show that P is also the altitude from P3. And so all of them meet at one point. So that's pretty simple because now we can just take these two and formulate a condition like this. So let's go ahead and do that. I'm going to switch colors. So v2 dot v3 is equal to v1 dot v3, and so v3 dot v2 minus v3 dot v1 is going to be equal to 0, and so v3 dot v2 minus v1 is going to be equal to 0. And so there we have it. That means that v3 is perpendicular to v2 minus v1. Okay, now so that's problem 2 done. Why don't we move on to problem 3? So it says 4 vectors are erected perpendicularly to the 4 faces of a general tetrahedron. Each vector is pointing outwards and has length equal to the area of the face. Show that the sum of these 4 vectors is 0. And as a hint, it mentions let A, B, and C be vectors representing the 3 edges starting from a fixed vertex. Express each of the 4 vertices in terms of A, B, and C, and show that their sum is a 0 vector. Do not introduce a coordinate system. So that last part is important because it is very tempting to introduce a coordinate system, but as I found out while solving this, it's far easier to do it without. And I did try with a coordinate system for a little while. So if we draw a tetrahedron there and we take this as a common vertex. This is our vector A, this is our vector B, and this is our vector C. So let's start by looking at the direction, right? So we know that I'm just going to do that in white. A cross B represents a vector going like that, which is perpendicular to this plane. And we don't exactly know the magnitude, and we know that that has to be equal to the area of the face, but we'll come to that back to that in a little bit. We know that, so I'm just going to label that A cross B. Why don't we look at A cross C? Now the thing with A cross C is that it's actually going to be pointing inward, and we don't want that, so we actually have to take C cross A. So this is going to be C cross A, and then this is going to be B cross C. And those are 3 of our vectors, and the 4th one, so for the 4th one we're going to have to take the cross of the vector I'm highlighting in yellow, and the second vector I'm highlighting over there. So the first one there is just going to be B minus A, and the second one is going to be B minus C. And so if you take the cross product of these two, then you'll find that because B cross A is pointing in this direction, and B minus A is pointing in that direction, and B minus C is pointing in this direction, sorry, no, the other way, then you will actually get a vector pointing outwards over there. So we need to now look at the magnitude aspect of it. So we know that the determinant of A and B is going to be the same magnitude as A cross B. And we know that the determinant represents the area of a parallelogram. If we draw two vectors A and B, then the area there is going to be represented by the determinant of A and B. And so we know that that area is also represented by A cross B. And if we want to find the triangular area, then we just take half of that. And so the actual magnitude is just going to be A cross B by 2 in this example. So we now have enough information to actually start solving it, because if we try to sum up the vectors, so we have our first vector, which is A cross B, and we now divide that by 2 because we want the vector's magnitude to be the area of the triangular face over here. We add C cross A. I'm going to move this a little bit. And we add B cross C by 2. Now we can add B minus A cross B minus C, the ones I've done in yellow, and this expands out to B times B, so B cross B minus by 2 minus A cross B by 2 plus A cross C by 2 and minus B cross C by 2. And so you'll notice that this term cancels out with this term, and this term cancels out with this term. Now what we have left is C cross A by 2 plus B cross B by 2 plus A cross C by 2. Now we can use vector properties to figure this out, because we know that A cross C is actually equal to minus C cross A. And so these terms will cancel out. And then any vector cross itself is just going to be 0. So we know that the sum of all of this is going to be 0. And that is indeed what we were expected to show. So that's all for today, and if you do have any questions, please mention them in the comments. These are my own solutions, but of course this is from an MIT course, so I don't have copyright ownership over this. But thank you for watching.